right, our next one here show that every member of the family of functions of this equation is a solution to the differential equation shown. By family, again, what they mean is that they're kind of saying whatever equation has this general form to it, plus what this constant could be something different. So no matter what the constant is, that would still make it a member of this family. And so what we want to show here is just in general that no matter what that C is, it's going to work. In order to do that though, not only do we need a y value, but we also need, looks like, first derivative. So let's find the derivative of this. So if we find the derivative of this function, we got natural log of x plus c over x. That's going to require us to do quotient rule. So we got low d high derivative of the top, derivative of ln x is 1 over x, plus a constant derivative constant would be 0, minus the high function, times d low, the derivative of x is 1. So if you want to put times 1 there, or just not put anything, that's fine too. Just like here, we don't really have to put the plus 0 on there. And then all over, when you're doing quotient rule, all over the low function squared. All right, so let's see if we can simplify that. If we multiply x times 1 over x, that's just 1. Here on this next one, just make sure you do distribute that negative sign. So we got minus natural log x minus the constant all over x squared. So that's our first derivative. So now what we're going to do, we're going to start with our differential equation here, which is this. And we're going to substitute now in our derivative and our y function. So our derivative we just found is 1 minus natural log x minus c over x squared plus x times, now our function is natural log x plus c over x. And it should equal 1 if this is a solution. So let's see if we can simplify now. It looks like these easily cancel out here and here. So now we got 1 minus natural log x minus c plus natural log x plus c here. Well, again, we got some easy simplifying. Our constants cancel, natural logs cancel. Only thing left then is that 1 equals 1. So yes, this one does check out. Doesn't matter what the constant is, anything in this form over here should be a solution to this differential equation. All right, so next, what they want us to do is illustrate A by graphing several members of the family of solutions on a common screen. So let's just pick some here to use in a graph. So we just have to pick different C values. So let's maybe do, if C is 7, then our equation is going to become y equals natural log x plus 7 over x. Let's go with a 4. So if C is 4, then that would look like that. Let's say maybe 2, if C is 2. It would give us that one. Let's go a fraction here. Let's do half. And let's get a negative 1 in there. Let's go -3. So then it would come out to be that. So what I'm going to do next is graph all of these out on a common screen to do that. So on the calculator, go into your y equals, and I've already preloaded and entered these in. To graph this, I know natural log x, you can't input any negative numbers or 0 for that, so this is going to be a positive graph. So on my window here, I started at x equals 0, knowing that we're not going to have any negative ones, and I went to 5, and then I made sure my y value were big enough here. Now let's graph these out on a common screen. All right, so here's what they look like. This is the graph of all these. If you hit the trace button, you can see which functions these are. So this one on top is, that was the one with +7. So this blue one, the graph kind of looks like this, and it keeps getting closer there. Our next one down, if you hit the up and down arrow, that's the +4 one. So this green one kind of does the same thing, but it kind of goes down more here. The next one looks like that one's the +2 one. Now this one, a little bit different. That one doesn't start at the top. That one actually comes from down here. Gets up here and then kind of goes like that. The next one we have, if I go down, that's the one that had +0.5. So this one also starts from down below. It starts down here. And that one kind of goes more like that. And then our last one's our negative one there. That one starts below, never goes above the x-axis, but also kind of goes that way. So that's the graph of all these. You can see all the graphs, no matter what, in the long run, do approach 0 here. All these graphs are approaching the x-axis. But depending on where you start, they do have different starting points here. It looks like some of these bigger C values, we actually start up here. Somewhere between 4 and 2 now, they start actually coming from the bottom up. It looks like as long as you're positive, you go up above the x-axis at some point. If you're negative, it stays below the x-axis. But again, still in the long run here, we'll go towards 0. So that gives you an idea of the different solutions. And this kind of stuff, this kind of is what you see when you get into maybe like some meteorology type stuff on weather patterns and systems of what storms might do based on pressure systems and that kind of thing. All right, last part to this question. Find a solution of the differential equation that satisfies the initial condition y equals 1. Well, so what we want to do now is take our function that we've been using here, ln x plus c over x, and if we want to find y of 1 equals 2, that means here we want to, if we plug 1 in for the x's, what does our initial condition come out to be? Okay, so whoop, I also need to plug 1 in for this x. All right, so what we know now is y of 1 does end up equaling 2. So let's plug that in here. And natural log of 1 is 0 over 1, which this will end up, 0 plus c is just c divided by 1 is just c. So our constant in this case would be 2. So if you have the initial condition of 1, that means this equation is going to turn out to be natural log x plus 2 over x. And that's one of them we had already graphed. And just to show you here, go back to our graph, and we find that one that had the, whoop, there it was, plus 2. If we trace along here, let's see if it'll let me trace. I don't know if it'll get right at 2 or not. Oh, looks like I'll have to do it this way. If you go to calculator, you can evaluate the value here. So I'm going to evaluate this one at 1. And you can see that, oh, wrong one. There we go. On this graph where it is, where the constant does end up being plus 2 there, you can see 1, 2, it does pass through that point on the graph. So that went through that point, it would end up having the constant of plus 2. No other member of that family is going to pass through that. So only this one where c equals 2 is going to pass through the point, or pass through this point here of being at over 1 and up 2. So that that's how you can find, if you have initial condition, you can figure out the exact differential equation there.